Our second lecture is related with the system of linear equations. System of linear equation means we have a set of equations which are linear. Here we will start from the system of linear equation. Here is the definition of system of linear equation. It is a finite set of linear equations when the variable x1, x2 up to xn is called a system of linear equations or a linear system. It may be written like that: a11x1 plus a12x2 plus dot dot plus a1n equal to b1. Second equation is a21x1 plus a22x2 plus a2nxn equals to b2. After last equation is am1x1 plus am2x2 plus dot dot plus amnxn equals to bm. So here we have the m equations with n variables, where aij are the coefficients and bj is the constants. So x1, x2 up to xn denote the unknowns in the system. If bj equal to 0 for all j, the system is called homogeneous. Otherwise, it is called non-homogeneous. What does it mean, the solution of the system of equation? By solution to the above system, we mean an order n tube of scalars substituted x1, x2, x3 up to xn, and to the left hand side it yields the values on the right hand side. Then the set of numbers is called the solution of the system. So if that number does not satisfy the left hand side equal to right hand side, so it means that set is not the solution of the system of equations. For example, here we have 4x1 minus x2 plus 3x3 equal to minus 1 to the first equation. Second equation is 3x1 plus x2 plus 9x3 equals to minus 4. So here we have a system of equation. If we replace the values of x1 equal to 1, x2 equal to 2, x3 equal to minus 1, so since these values satisfy these two equations, so it means these values are solution for the given system of equation. However, if you plug in x1 equal to 1, x2 equal to 8, x3 equal to 1, it's not a solution since it satisfies only the first equation. However, if you plug in x1 equal to 1, x2 equal to 8, x3 equal to 1, it is not the solution since it satisfies only the first equation. So what does it mean? It means a sequence of numbers is called the solution of a system if it satisfies the left hand side equal to right hand side. Exercise: verify that the given triple of real numbers is the solution of the system of equation. So if we replace in place of x1 equal to 1, x2 equal to minus 1, x3 equal to 2 in these three equations, so if first equation answer 13, second equation answer is minus 2, and third equation answer is 3, so it means left hand side values are equivalent to the right hand side values. So it means that set of triple numbers 1 minus 1 comma 2 is the solution of this example. But if you plug in second example 2 equivalent to x1, minus 3 equivalent to x2, 1 equal to x3, and if you replace these values in four equations. So if we put these values in first equation, we will obtain that 2 minus 3 minus 2, 2 minus 3, 2 minus 3 minus 2. What, what is the answer? 2 minus 3 minus 2. Answer. Answer is minus 3. So it means the left hand side equal to right hand side. Similarly, if you put x1 equal to 2, x2 equal to minus 3, x3 equal to 3, x3 equal to 1 in second equation. So the answer is 6 minus 3, 6 minus 3, 3 minus 7, 6, 6 plus 3, 9, 9 minus 7 equal to 2. So it means left hand side equal to right hand side. Similarly, if we put x1 equal to 2, x2 equal to minus 3, x3 equal to 1, what should be the answer? Answer is 2 minus 3 minus 1 plus 1 equal to 0. It means left hand side equal to right hand side. Similarly, if you put x1 equal to 2, x2 equal to minus 3, x1 equal to 1, the answer is minus 6. So it means it satisfies all four equations, so that triples is the solution. It is the exercise to write coefficient matrix, augmented matrix, constant vector for each of the following examples. Here you see the first example is x1 plus 2x2 minus 3x3 equals 1, 2x1 plus 4x2 minus 5x3 equals to 2, 7x1 plus 2x2 minus x3 equal to 3. This is example 1. You have to write the coefficient matrix A, the constant matrix B, and the augmented matrix A hash. In second example, x plus y plus z minus w equals to 3, 2x plus 4y minus 3z plus 7w equals to 2. You have to write here the coefficient matrix A, the augmented matrix A hash, and the constant matrix B. This is a third example. x1 plus 2x2 minus x3 equals to 0, 2x1 plus 3x2 minus 2x3 equals to 0, 5x1 plus 6x2 minus 5x3 equals to 0. So here you have to write coefficient matrix A, the augmented matrix A hash, and the constant vector B. Consistency of the system of linear equation. What does it mean, consistent system? A system of equation that has at least one solution, it is said to be consistent solution. But if a system of equation that has no solution is said to be inconsistent system. For example, let us suppose here we have two equations, x plus y equal to 4. Second equation is 2x plus 2y equal to 6. If you multiply second equation by half, the answer is x plus y equal to 3. So if we solve these equations, we does not obtain any type of solution. So such type of system of equation is called inconsistent system. There are three types of possibilities of the solution. For example, if you have two linear line equations, a1x plus b1y equal to c1 is first line equation. a2x plus b2y equal to c2, it is second line equation. So if both lines are parallel to each other, so it means system does not have any type of solution. But if these two lines are intersect at one point, so it means the system has a unique solution. But if both lines are overlapped each other, so it means system has infinite many solutions. So there are three types of solutions in system of equations. First type of solution is called unique solution. Second type of solution is called infinitely many solutions. And third type of solution is called no solution. The types of you may denote these three types of solution as no solution, exactly one solution, or unique solution, or infinitely solution. In order to find the solution set, we must write the system of equation into matrix form. For example, here we have the system of equation a11x1 plus a12x2 plus dot dot plus a1 and xn equal to b1, which is first equation. a21x1 plus a22x2 plus dot dot plus a2 and xn equal to b2. And the last equation is am1x1 plus a2x2 plus dot dot plus am and xn equal to bm. So it may be written in the matrix form, that is a11, a12 up to a1n b1, a21, a22, a2n b2, am1, am2, amn bm. So you know here that we write here both coefficient as well as the constants. Coefficients are in terms of aij, the constants in terms of bj. So if we write both type of values in one matrix, so that matrix is called augmented matrix. Example, here we have x1 plus x2 plus 2x3 equal to 9. That is first equation. 2x1 plus 4x2 minus 3x3 equal to 1. 3x1 plus 6x2 minus 5x3 equal to 0. It may be written as in the matrix form, that is 1, 1, 2, 9. That is first equation. Coefficients of the second equation is 2, 4 minus 3, 1. And the coefficient of third equation is 3, 6 minus 5, 0. So that matrix is known as the augmented matrix. Augmented matrix is very useful not only in finding solutions but also in finding different other concepts of linear algebra. The most important concept of linear algebra is finding out the eigenvalues and the eigenvector, where we must write the system of equation into augmented matrix form. So therefore, we may say it is very important matrix called augmented matrix. Solving a system of equation. We may apply different ideas to solve the system of equation. For example, Kramer rule is one of the idea, or for example by using simultaneously solving equations, we may obtain the solution or solve the system of equation. But these ideas are limited to very low number of equations. But if we have huge number of equations, we must apply that idea of elementary row operations. So the main idea is here is to replace the given system by a new system that has the same solution set but which is easier to solve. We apply the following three types of operations called elementary row operation to eliminate unknowns systematically. Multiply an equation by a non-zero constant. This is first operation. Second operation, interchange two equations. Third operation is add a multiple of one equation to another. These operations correspond to the following elementary row operation on the augmented matrix. So multiply a row by a non-zero constant. It is the first elementary row operation called multiplicative row operation, and it may be written, or symbolically it may be written as m subscript I bracket k. Interchange two rows may be denoted by permutation ij, where I interchanged by row j. Third operation is called addition operation. Here we add row number I by k, and the answer is added in row number j, and it is also stored in row number j. These three types of operations are known as elementary row operations. In this example, we are applying elementary row operations to the system of equations. Here we have the system of equation is x plus y plus 2z equals to 9. Second equation is 2x plus 4y minus 3z equal to 1. Third equation is 3x plus 6y minus 5z equal to 0. We are interested to find out the values of the three variables x, y and z. So first we apply here in order to get the solution by using elementary row operation. Here we apply first elementary row operation called addition. In this operation, we multiply row number 1 by minus 2 and add the answer to row number 2, and the result is stored in row number 2. So you see here the answer is stored here, 2y minus 7z equal to minus 17, or 0 2 minus 7 minus 17. So that is what? That is the second row. After applying that operation a1 to minus 2, so we get the answer in row number 2. This row is 2y minus 7z equal to minus 17, or in matrix form it is 0 2 minus 7 minus 17. So here we again apply the addition operation. Multiply minus 3 to row number 1, and the answer is stored in row number 3. So you see, if you apply row number 1 by minus 3, so answer is minus 3, minus 6, minus 27. And if we add to row number 3, so minus 3 plus 3 equals to 0. You see here 0. And minus 3 plus 6. Minus 3 plus 6 is 3. Answer is stored in row number 3. Again you see minus 6 plus minus 5. Answer is minus 11. You see here. Third operation is, if you multiply 9 by minus 3, the answer is minus 27. And answer is stored in row number 3. So we obtain that matrix here. We see here the answer. Finally we find out this matrix 1 0 0, 1 2 3, 2 minus 7 minus 11, 9 minus 17 minus 27. So now we again, in order to get the solution, but to get the key one element here, we multiply row number 2 by half. Row number 2 by half. So we will obtain here y minus 7 upon 2z equal to minus 17 upon 2, or in matrix form it may be written like that, 0 1 minus 7 upon 2 minus 17 upon 2. Why we do this? Because we want to get the key element 1 here. So if you multiply 1 by minus 3, here see, if you multiply row number 2 by minus 3 and add it to row number 3, so that element become equal to 0. So we want to make that element equal to 0, right? So if you multiply row number 2 by minus 3, row number 2 by minus 3 and add it to row number 3, we will obtain that row minus half z equal to minus 3 upon 2. Or in matrix form 0, 0, minus half minus 3 upon 2. So finally, if you multiply row number 3 by minus 2, row number 3, here you see row number 3 by minus 2, so minus minus plus 2 to cancel, the answer is 1 here, minus minus plus 2 to cancel, answer is 3 here. So now finally we obtain this equation. So that matrix is lower triangle type matrix. Here one denote the variable x3 value, so x3 equals to 3. Then x2, if you substitute backward in this equation, will obtain the value of x2. Again, if we plug in these two values of x2 and x3 in first equation, we will obtain the value of x1. So finally, we obtain that matrix after applying elementary row operations. We obtain here these three equations: x plus y plus 2z equal to 9, y minus 7 upon 2z equal to minus 17 upon 2, and z equal to 3. Or it may be written like that: 1, 1, 2, 9, 0, 1 minus 7 upon 2 equals minus 17 upon 2, 0, 0, 1, 3. Right? Again, if we apply here the add operation, second row, if we multiply second row in order to make it equal to 0, we multiply second row by minus 1 and add it to the first to obtain. So here we multiply row number second row by minus 1. So it becomes minus y plus 7 upon 2z equals to plus 17 upon 2. Right? You see? And add it to first equation. We will obtain here on x plus 11 upon 2z equals to that. In order to further simplification, we again apply here the add operation. In order to that become 0, that element becomes 0. So if you multiply again the third equation by minus 11 upon 2 and add it to row number 1, we will obtain x equal to 1, y equal to 2, z equal to 3. So finally we obtain that solution, that is a unique solution, is x equal to 1, y equal to 2, and z equal to 3. So these elementary row operations you may apply on n by n matrix, whether we have 50 equations or 100 equations. We may apply these elementary row operations in order to get the values of the variables for linear system of equation. So it is very beneficial to find out the solution of n by n system of equation. Here is the exercise. For this topic of the system of equation. In question number 1, you have to find the solution of each of the linear equation. So by putting the value of y, you may obtain the value of x here. Similarly, we will plug in different values in order to get the value of x1. So you see, all four equations are linear equations, and we are interested in to find the values of x and y. To try this one, if any problem you may ask. In question number 2, we have to find the augmented matrix, or so that example A, you just write it in augmented matrix form. In augmented matrix form, you write these coefficients along with the constant minus 1. In second row, you write here the coefficient 4, 5 along with the constant 3, 7x, 7 and 3 equals, on the right hand side you must write here 2. Similarly, in part B, you have to write the augmented matrix, and CD you again. So in this question you write the equation form into matrix form. In question number 3, it is the inverse of question number 2. You have to write an equation form. What is the equation for that one? That equation is 2x1 plus 0x2 equals to 0, 3x1 minus 4x2 equals to 0, 0x1 plus x2 equals to 1. Here you may see an equation form. It may be written like that: 3x1 plus 0x2 minus 2x3 equals to 5, 7x1 plus x2 plus 4x3 equals to minus 3, 0x1 minus 2x2 plus x3 equals to 7. In C part, you know, it may be written as in equation form. In equation form, it may be written like that: 7x1 plus 2x2 plus x3 minus 3x4 equals to 5. Here you see answer is x1 plus 2x2 plus 4x3 equal to 0x4 equal to 1. So these may be the two equations. And in part D you see in equation form it may be written like that: x1 equals to 7, x2 equals to minus 2, x3 equal to 3, x4 equal to 4, right? So these are the system of equation form from augmented matrix. In third question, find a linear equation in the variable x and y that has a general solution x equals to 5 plus 2t and y equals to t. In this question you have to find the linear equation, try to solve it. And question 4 and question 5, here we have the curve. In figure 2 you see this, that is a figure 2, passes through the points. These are the points here. Show that the coefficient a, b, c are the solution of the system of linear equation. So by using augmented matrix, try to solve. Now next concept is which is very important concept called echelon form. So there are three. Echelon form is very important in other concepts of linear algebra, as well as in order to find out the stability of the system, we must convert the system of equation into echelon form. It is very important concept. Here you see that form is called row reduced echelon form. So there are four conditions of reduced echelon form. That if a row does not consist entirely of 0, then the first non-zero number in the row is a 1. You see, in first row, first non-zero element of that row is 1. That 1 is called a leading one. If next condition is, if there are in second row, if there in second row you see the first non-zero element of that row is 1, and in third row the first non-zero element is 1 here. So that means that matrix satisfies the first condition. Second condition is, if there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. So in this matrix there does not exist any zero row. Any row that consists entirely of zeros, there does not exist such type of row in this matrix here. In third condition, here you see in any two successive rows, that means two successive rows that do not consist entirely of zeros and entirely of zeros, the leading one in the lower row occurs further to the right than the leading row in the higher row. You see the right right than the leading row in the higher row. It is right on the leading row on the leading row in the higher row. You see, here is 1, it is on the right on the leading row on the higher one. Next condition is each column with a leading one has zeros elsewhere. So you see that the leading one for this column and else numbers are 0, and leading one only 1 and other elements below 1 0, and this one similar. So if any matrix satisfies these four conditions, so such form is known as echelon form. That concept is very important, not for examination point of view, but also for practical point of view. You may apply this concept in various applications of engineering. Echelon matrices, you see, if a row does not consist entirely of zeros, then the first non-zero element number in the row is 1. That is the definition. If any matrix satisfies these four conditions, so you may say that matrix is echelon matrix, echelon form of the matrix, right? So these four conditions are: if a row does not consist entirely of zeros, then the first non-zero number in the row is a 1. That is called leading one. If there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. Third condition is in any two successive rows that do not consist entirely of zero, the leading one in the lower row occurs farther to the right than the leading row in the higher row. Each column with the leading one has zeros everywhere else. So any matrix having properties 1, 2 and 3 but not necessarily 4 is said to be a row echelon form. A matrix having properties 1 to 4, 1 to 3 and 4 is said to be reduced row echelon form. There are different examples of reduced row echelon form and row echelon form but not reduced row echelon form. So it is an example of reduced row echelon form. Why we say it is reduced row echelon form? Why? Because that matrix satisfies all four conditions. See, all columns having here all columns leading ones. This is first leading one of the first row. In second row, it is a leading one for second row, and it is a leading one for third row. And the lower row leading one is on the right of the higher row, and third row leading one is on the right of the second row. So it satisfies all the conditions of reduced row echelon form. So that's why you may say it is called reduced row echelon form. It is also reduced row echelon form since it satisfies all four conditions. It is also satisfying all four conditions of reduced row echelon form. So you may say it is also the example of reduced row echelon form. It is also an example of reduced row echelon form. So these four matrices all are satisfying four conditions of reduced row echelon form. So you may say that these matrices are reduced row echelon forms. And the next matrices are, you see here, the following are in row is not reduced row echelon form, but it is only in row echelon form. You know the difference between these two forms. That form is reduced row echelon form, and that form is called row echelon form. We already find we already know the definition of these two forms. So here you see one leading one on the first row. It is a leading one for the second row. It is a leading one for the third row. And below leading one, other elements are 0. Below leading one, other elements are 0. Right? Here is nothing below that from that one. So that matrix is called row echelon form. It is also row echelon form. It is also row echelon form. But these matrices are an example of reduced row echelon form. Here is an example. Here you see is an example of raw reduced echelon form, since it's satisfying all the condition. Suppose that matrix is augmented matrix. After applying elementary operations, we may obtain such type of matrices. In that matrix, here you see the value for x1 equal to 1, x2 equals to 2, x3 equal to 3, right? So by using Roy reduced echelon form, we may obtain the solution of n by n matrix system of linear equation. Consider here this example, raw reduced matrix here, it's satisfying these four conditions. We may say it is an example of raw reduced echelon form, since x1, x3 and x4 correspond x1, x2, x3 and x4 correspond to leading ones, in the augmented matrix. We call them leading variables. The non-leading variables are called free variables, right? Solving for the leading variables in terms of free variable, we obtain x1 equals to minus 2 minus 6x2 minus 4x5. From second equation, x3 equals to 1 minus 3x5, x4 equals to 2 minus 5x5. Finally, set in order to get the solution for all the variables, we must suppose here the free variable, that variable, since it is, you see, all elements are equal to 0, but it is missing here. Which variable is missing here? The missing variable is x5. x5 is missing, so we must suppose that that variable is called the free variable, right? And free variable is such a variable where there does not exist any leading one. So here you see there does not exist any leading one, so we must suppose the value of x5 equals to any unknown. So you see, we suppose here x5 equals to t, and another free variable is x2. Since x2 position is missing here, we again suppose x2 equal to s, and putting these two values in above three equations, we may obtain that type of solution. x1 equals to minus 2 minus 6s minus 4t, x2 equal to s, x3 equals to 1 minus 3t, x4 equals to 2 minus 5t, and x5 to t. So here you see we have the values of s and t are infinite. So if you plug in infinite values, you may obtain infinite solutions for the variables x1, x2, x3, x4. Next example, consider the raw reduced matrix here. Since it's satisfying all the condition, also that matrix is also called raw reduced matrix. The last equation is, you see, or you may say it is augmented matrix also. In the last equation, see 0x1, 0x2, 0x3 equals to 1, which is not possible. So it means there does not exist any type of solution for that augmented matrix. Or in other words, you may say that matrix showing the inconsistent system of linear equation. Gaussian, that is another example, that is augmented matrix here. You see, so we are interested in to find the solution for these variables x1, x2, x3, x4, x5, and this is equal to 12. So by applying different operations here, elementary raw operations, we may obtain its solution. So first we convert that matrix into reduced echelon form. So you see here that is the reduced echelon form. That is reduced echelon. After applying several raw operations, we may obtain that form called raw echelon form. Finally, we obtain that reduced raw echelon form. So that is the position of x1, that is x3 and x5, and other all variables are equivalent to treating as the free variables. So that method is called Gaussian elimination method, where we applying elementary operations in order to convert the augmented matrix into raw irreducible form. That matrix is called augmented matrix, and that method is called Gaussian elimination method. But if we convert the augmented matrix into reduced raw echelon form, such method is called Gauss-Jordan elimination method. So that is the only difference between two methods. One difference is that we first convert the augmented matrix into raw reduced echelon form, and in second method we convert it into only raw echelon form, not reduced raw echelon form. So that method is called Gaussian elimination method.